Morning, Brendan.
Good morning.
How you doing? Our final class here.
Doing well. How are you?
All right, we have some funny topics to talk about today.
Oh yeah.
Some confusing things going on in the world of astronomy and cosmology.
Yeah.
Yeah.
Are there a lot of professors on campus?
No,
No, just you.
hardly anybody. No, I don't know if it's not just me, but certainly I do feel very lonely. No. It's actually fine. I get work done here. I don't work very effectively at home.
Oh no, neither do I. It's
It's too
terrible.
relaxing and distracting. So,
Yeah, I need that separation.
well, I think, I don't know. Do you find a way to do it then? What do you do?
Power through it eventually.
Power through it. I mean, we only have one more week, so
Yeah.
gotta find a way. But yeah, are you taking classes during the summer?
No, I'm not.
Okay,
I'm gonna continue tutoring physics over the summer.
awesome.
And then I'm transferring in the fall. So I
Very
just gotta
good.
plan all that out.
Congratulations. Where are you gonna go?
So far I've gotten accepted to UCSB, UCSD, and UCLA.
Wow, very good. And what are you in, physics or engineering?
I was trying it's kind of new actually. It's called engineering physics.
Okay.
And there's only a couple schools that offer it.
Uh-huh.
UCSD is one of them.
Okay.
So I was gonna try for that, but I'm still waiting. I applied to a couple of private schools too, so I'm still waiting to hear back from them.
All right. Well, that's awesome, dude. That's great.
Yeah.
Well, it sounds like you've already got some good options. Actually, I went to UCSB. I can tell you it's fantastic. The undergraduate program is actually better than some graduate programs around, that I've been to. So,
Wow.
I mean, I left as an undergraduate from UCSB and went on to graduate school, and I found I went to a couple different schools, and I found that it was kind of easy compared to my undergraduate training. So.
Really?
Yeah, they really prepare you well. But UCLA is great, UCSD, they're all really, well-known programs. Good morning, everybody. Good morning, Leone. Nice to see you guys. Thank you for joining me. I was wondering if nobody joined me, what would I do? And I just kind of talk, I guess. But anyways, it's more fun if you guys have your some reaction, because some of the topics we're going to talk about today are a little bit strange. Hello, Fanny. Wonderful. Haven't seen you here. Thank you for coming. So yeah, this is our final class. And I guess one of the things I should also talk about is what we're going to do with the final exam. You guys might be curious. I didn't know what I was going to do until, well, I still don't quite know, but I have an idea what I think is, fair, and we'll go ahead and do that. Anyways, well, good morning, everybody. And we do have a number of interesting topics to finish up with. And the truth is, for some of them, I don't really know the answer. In fact, there was another, wow, I should add that on. Yeah, I might as well, because it's something that's very relevant to what we've been talking about, is an article just came out a few days ago that we'll bring up. We'll talk about that in a minute. Okay, so let's see. Good morning, and let's see if I have anybody on YouTube. I have got a couple people on YouTube. If you're on YouTube, can you say hello, and just so I know who you are and who's there? Otherwise, let's see, I'm going to go ahead and spotlight my video. Okay, so we have, this is our last class. Wow, we made it. Okay, so I know this is not what I anticipated, and you didn't anticipate. So thank you for sticking with me. And I hope that you got something out of this class. And I guess I should save this till the end. But anyways, if nothing else, hopefully it's sparked your interest in learning more, not less, and understanding also that our understanding of the universe is growing and it's changing. And so what we think of as true may actually not necessarily be the entire truth, that there's more information that we still have to, find, right? When will we be done? When will we understand the truth? And science says never, right? We will never actually know the truth. We will only know an approximation of the truth. So let's just take a look at our canvas. I don't know what I can actually, what's on canvas? I don't even know if anything's on canvas. What's on canvas? I don't know. Nothing. Never mind. Okay, I don't know what to say. Okay, hold on. Let me just see if I put anything there. I don't think I did. So I didn't put anything. So that's a waste. Okay, never mind. So there's nothing on Canvas, but I need to put something on Canvas. So let me just talk to you for a second. Okay, so my plan is for the final exam, I think we were scheduled for Monday. Anybody remember if we were scheduled for Monday? And that would have been an in-class exam, 2 hours, right? And what I typically would do is make it, a few multiple choice questions, and then the rest is mainly essay. But I'm appreciative of how difficult this whole situation is for me and for you. So what I'm going to do is I'm going to do something a little bit different than I planned. I'm going to make it about half multiple choice questions and half essay. Okay, so it's a little bit heavier on the multiple choice. And the idea is I'm going to give you an exam that should be able to be completed in 2 hours. And I'm going to open it at 12:01 a.m. on Monday morning. But I'm actually going to give you, if you don't feel quite ready, I'm going to give you until Wednesday at midnight to do the exam. You can do it at any time between Monday, 12:01 a.m. and so did everybody hear me? Okay, so Monday, so the final exam, I'll write this down, final exam, 50% multiple choice. And are there any calculation type of problems? Very, very few. This is much, much lighter on the calculations, but there is a little tiny bit of math. And if you look back at the topics that we've covered since the midterm, you'll find out there are just a very, very few things that we actually talked about. So short answer. So short answer will include any calculation type of work, okay? So maybe a calculation, but not much. Okay, this is not going to be like relativity and all that stuff that we did before. Can you read that? Okay, calculations. There may be some. Okay, and then it will open at 12:01 a.m. on Monday. What's the date on Monday? Anybody remember? 2nd, 3rd, 4th? Monday the 4th? No, Monday the 6th. What the heck? No, Monday the 4th, sorry. Monday 5/4 and close. So please be done by on Wednesday 5/6. Okay. All right. Any questions about that? You guys know your final exam. What is it going to include? Half multiple choice, half short answer questions. And I mean, there's plenty of topics for me to pick. So I may even, I don't know what I'm going to do exactly. I'm still writing that. I haven't written your exam yet. So I'll be writing it this weekend, having fun. Anybody have questions? Could raise your hand or say something. Anybody? Good morning, everybody. Say good morning in the chat if you want. I know you're not here in person, but I hope you're remembering to be patient with everybody, because everybody's a little bit stressed and everybody's getting tired of being in quarantine. And we've been doing really well, right, in terms of Santa Barbara County and the number of people that have been, have died from it. It's very, very small. But, we want to continue to not have people die from this. So thank you for sticking with this, okay? I appreciate that, because I'm a cancer survivor. I'm actually at high risk. Oh, I hope I don't die. No, I'm just kidding. I'm not going to die. I'm not going to die. All right, so let's see. Let's go ahead and talk about some cool stuff. Okay, this is some fun topics that we're going to have for our final day. And I promise you, I don't know the answers to all of these. In fact, there may not even be an answer that a human can answer at this moment. But let's try and see what we can see. So this is one of the things that I mentioned to you. See, for example, for our next class, we're going to discuss the current problem with the Hubble constant. So this is an article that, this is a NASA article. And let's take a look at that. Did anybody read the NASA article? Take a look. Anybody? All right. So astronomers have made, can you guys all see this? Can somebody let me know you can see this?
Yeah, I can see it.
Okay, great. Thanks, Lenny. Okay, so the new Hubble constant measurement adds to mystery of the universe's expansion rate. So astronomers have made a new measurement of how fast the universe is expanding, the Hubble constant, using an entirely different kind of star than previous endeavors. The revised measurements, which comes from Hubble, falls in the center of a hotly debated question in astrophysics that may lead to a new interpretation of the universe's fundamental properties. Okay, so they're looking at what is this research? You should probably know this. You know, what did they use, right? They're looking at something. What are they looking at? These galaxies are selected. They're comparing the galaxy's distance to the apparent rate of recession due to the relativistic effects of expanding them. By comparing the apparent brightness of the galaxy's red giant stars with nearby red giants whose distances were measured with other methods. So this is actually called a anybody remember the name of this? This is a spectral. There's a name for this. Okay. Anybody remember the name? How do you, it's called, shoot. It's main sequence fitting. Oh, it's not main sequence fitting because they're red giants. Okay, so I don't know what this is. This is a technique that I don't know about. So this is, it's like main sequence fitting. So you're using similar red giants and then you're comparing, and why would they use red giants? Anybody have an idea why they might use red giants? Any reason why you would use a red giant over another kind of star? Okay, so if you don't know, red giants are pretty luminous. They have a lot of light coming out of them because they're so large. So even larger are red supergiants. So maybe somebody has done that as well. But I think that maybe the reason they use red giants is these are like our sun, for example, is in the last stage of its life will be a red giant. So they last for a while, which means the population should be larger. One of the problems with red supergiants is they don't last very long, and therefore there's going to be a lot less of them to use. So I guess that would be one of my rationales for why they're using red giants. Okay, if I ask you a question today, why would you use a red giant over a red supergiant? And even though red supergiants are more luminous, there aren't very many of them. So using more red giants would be better. Okay, so this measurement is slightly smaller. So what was their measurement? Okay, they just under 70 kilometers per second per megaparsec, okay? And then this is smaller than what was done with Hubble's shoes, which is supernova. I don't know what that is, H0. I don't know what that means. Oh, Hubble constant, that's H0, okay? Using Cepheid variables. Okay, cool. All right. Anyways, okay, so here's the big problem. Okay, so you have now a measurement which is using stars and the Doppler effect. This is the Doppler effect. And these stars are relatively nearby. Okay, these are relatively nearby. I mean, they might be really far away, but the fact is, you know, they're close enough that we can measure their Doppler effect. They're relatively close. The second major technique, categorically different technique, is the one that was undertaken by Planck, the Planck scientists, okay? And this one uses the microwave background radiation. Make sure you know that. Cosmic microwave background radiation. And this one, they calculated the value of 67.4. So at first glance, it's like, well, these numbers are different. But remember that there's more to a number in science than just the number that they state. There is also the uncertainty, right? How much value, how far can it be from this central value, this average value, this best value? And so the question is, do these disagree? And the answer is, well, actually they do. And these numbers are significantly different, right? And so the question is why and how and what's going on, all right? So anyways, that's just an example of an article. If we go to the, sorry, let me just go back to, any questions, by the way? Did you hear the difference, right? So one is using stars and Doppler effect, and the other is using the cosmic microwave background radiation. Okay, so they're significantly different techniques, okay? Okay, so let's take a look at Wikipedia. This is an awesome article showing you, and actually, if you jump down to this page is actually a lot of information, way too much. Actually, it's really cool. If you're just curious, you can read. It's wonderful. A lot of really interesting information. Much of it is beyond our course. It's just too much, and has some really cool symbols and math. And anyways, this is actually a pretty cool thing. So this is, take a look right here. Actually, I didn't mean to do this, but since I'm here, let me go ahead and talk about it. So what do you notice right here? You can see that these are distances measured in megaparsecs, and they go out to about 20. So the point is, these are relatively close to us, 20 megaparsecs, okay? Can anybody tell me why I'm saying that's close? What is a potential distance that you and I might talk about? What's a potential distance? How far away can a galaxy be? Maybe you're not sure. This is millions. Okay. I'm not getting any input. I need somebody to talk. Anybody know? Why am I saying is 20 megaparsecs a small distance? It's not a small distance, but relative to the universe it is, right? So what does this mean? A parsec is 3.26 light years. So we're taking like 65 million light years away. Okay, 65 million light years away, which is kind of an interesting number, right? Because that's about how long ago the dinosaurs, not how long ago, 65 million years ago, the dinosaurs died in a sudden event. But anyways, this is light from 65 million years ago, right? But we know that there's a lot further away. Like how far away? Lonnie's got an answer.
Like how far away are some galaxies?
Well, why is this small? How far away can it be?
Well, we just found out that they can be. Well, I was kind of thinking about it like with how we're looking at the Hubble constant. We're guessing like it's currently 70 kilometers per second per megaparsec. So when you're saying it's only 20, that doesn't seem like very much compared to how big it could be. And I'm just trying to remember how far away that galaxy we talked about.
Right. So what was the distance on that galaxy we talked about? The furthest galaxy. What was that?
It was 10 to the third, I think. Or no, I forgot why I wrote it down. Shoot.
Anybody know the distance to the furthest galaxy?
32 billion light years away.
Okay. 32 billion light years, right? This is billion, this is million, right? That's 1,000 times more. Okay, anyways, maybe I made my point. Hopefully you understand. These distances that we're talking about for measuring the Hubble constant are coming from relatively close things. Now, I'm not saying that we can't do this with further things, but you can see that the distance that I'm showing right here is pretty small compared to what it can be, okay? And this is, you can see that there's a line, but also you can see there's some variation, okay? So that is notable. You wanna make sure you understand that, right? That's kind of notable. All right, so then we look and, you know, what does it mean? And even though Hubble constant is a very simple thing, it's a linear relationship, you can see that what's going to happen is that as you take into account different effects of relativity or not, the shape of the curve may not be linear after all, right? It may change and yeah. So anyways, remember that the letter Z represents how many times the speed of light we see that galaxy receding. right? And so we can see it moving faster than the speed of light, and it's not a violation of special relativity because it's occurring as a result of the expansion of space-time, not because of actual relative motion, right? Even though it looks like it's moving that fast, it's because of the expansion of space-time. Okay, so I'm in way too much, math here that we're not going to do, blah, blah, blah. This is kind of interesting. You can actually see the Friedman. These are the Friedman equations. Okay, so anyways, Olbers, but look at they talk about all the stuff that we should be knowing about. Okay, so here, this is actually a really nice, this is actually what I was going to tell you about. So here we have the best value. So in the middle, we have the best value. And you can see they're not super, well, they're pretty different, right? But the key part is, if you look 2011, 2012, these agree with each other. But again, these are telescopes. They're going to be based on observations of redshift. Then came out WMAP, which is an infrared coverage of the sky. And it's a huge survey, much bigger than these two surveys. So surveys mean you're going to cover a huge part of the sky. And again, they got a different value, but if you look with this large error margin, right, they weren't very confident that this value was exactly right. There's a large interval of uncertainty. So if you look at these three values, I would ask you a question and hopefully you know the answer. Do they agree or not? Okay, so if you haven't taken a lot of science, this might be a new idea. So it's important that I share this with you. How about someone who's taken other science classes? You've talked about a number with the uncertainty, a number with uncertainty, a number with uncertainty. Do these two values agree?
Oh yeah, those two totally do.
They totally do. Okay, because why? Why do you say that they totally do?
The majority of their margin of error is shared. So.
Okay, good, right? So you can say that they're almost lining up. This one's just a little bit higher than this one, but even the size of the uncertainty is similar, right? So you might say these two agree, but what about these three? Do they agree?
Well, not
in
so
science,
sure.
would you say that these agree or not?
I would say no.
Okay, so then you're misunderstanding something important, okay? As long as there's an overlap, they agree. That's it, you're done, okay? If they do not overlap, then they do not agree. But if you can find a place where they overlap, then they are actually not contradictory, okay? So this is considered to be agreement because there is a region where they overlap. All three of these experiments, even though they're not giving you the exact same result, within the error margins, they do agree with each other. So as long as there is a region of overlap, you're okay. In other words, you have not disputed your hypothesis, you have not refuted your hypothesis. But now, look what happened in 2013 when they finally evaluated the Hubble constant from the Planck data. This was a hard job, actually. This is a big theoretical job. What is the Planck mission studying? You guys remember I just told you a minute ago. Anybody remember?
Studying the cosmic background radiation.
Okay, the microwave background radiation, which comes from what?
The Big Bang.
From the Big Bang, right? So they studied the cooling of the universe that has occurred, and from that they derived the value of the expansion rate, right? The Hubble constant. So does this value agree with the other three?
Only one of them.
It only agrees with one. So if these experiments are valid and we have confidence in them, then we have a problem. So you need to know this is a big deal in cosmology today. These values do not agree. And I know this one agrees, but that's not enough. These are supposed to be really high quality experiments, okay? These are not just, first of all, the data sets were amazing. They were the biggest data sets that had ever existed. And so we have there was some confidence in this interval here. Okay, so now I've talked a little bit about it. I want you to understand the magnitude of this. This is a big deal. Okay, let's go down and you can actually see a bunch of different ways to measure the Hubble constant. Okay, so there are more than just one. And in fact, there are some new ones now too. Okay, so Hubble, pretty old, Chandra, WMAP, 3-year, 5-year, 7-year survey, all agree with each other. 9-year survey starts to show even better precision, or not precision, accuracy. So accuracy is, sorry, I'm gonna write that down. Okay, so actually, I even made a mistake sometimes, right? So when we say precision, what do we mean by that? Precision is the number of significant figures. And so if you're talking about the Hubble constant, it's the number of decimal places. Okay, accuracy is how well do the data points agree with each other, right? The size of the error bars. So if they're larger error bars, there's a lot of spread in the data. They do not agree with each other completely. Your accuracy will be a larger set of error bars. So precision is how carefully you place that central point, and the accuracy is how wide are these error bars, okay? Okay, so take a look, right? And you'll notice that as the WMAP survey went on, I can't see it. Well, actually, do you see that these error bars are closer together? I don't know if you can see that. These ones don't look much closer than this one, but this one and this one, if I compare them, this one has smaller error bars than this one. Can you guys see that? And then as it went even further, the error bar got even smaller. So more data leads to, or can lead to, a smaller error margin. You feel more confident in your data. But take a look at Planck, very small error bars because I guess because it's a lot of data. But you can see they don't all agree with each other. We have a problem, right? I do want to highlight for you something really crazy cool. I want you to look right here. Do you guys see what this says? Who can identify what technique was used to measure the Hubble constant?
That was gravitational waves.
GW, gravitational wave from the kilonova, 2017, August 17th, right? They used the data from the gravitational wave to estimate the Planck constant. Is that crazy? And you might be like, Sean, you know, look at the error bar right there. That doesn't really look very confident. But ladies and gentlemen, this is the first one. And how often are they getting gravitational wave signals now? On a daily basis. Do you know which technique may become the best technique for measuring the Hubble constant soon? Gravitational waves, right? Which is so exciting. We are beginning this brand new era of cosmology where we measure gravitational waves and discover how fast the universe is expanding. This is phenomenal. Okay, I'm super excited about it. But here's the problem. If you look at all these great experiments that feel very confident, you know, in their ability, oh, look, Planck 2015, I couldn't even see the error bars, right? This is how confident they are, right? And 2018 is even better. So as time went on, and I don't believe it's, oh, it might be new data. I don't know if it's new data. It might be new processing, but there's clearly a division, okay? They do not agree. These different techniques, which are supposed to be incredibly powerful. This guy, well, who is this, right? Di Valentino, man, that one looks funny. So anyways, what does this mean? We have absolutely no idea what's going on in the universe. I don't even know why we're trying. No, that's not what I want to say. I mean, it may be true, by the way, but I don't want to say that. I want to talk about like, what does it actually mean? So I actually have an idea. Maybe some of you can talk about it too. What is the big difference in the class of experiments that are being done, right? There are observations of receding galaxies, Doppler effect, Doppler shift, and then the other is cosmic microwave background radiation, right? They're two different areas, regimes, really very different. And yet they're still trying to calculate the same expansion value because the expansion of space-time governs all of this. So what could be the solution to this apparent quandary, right? This apparent conflict between the two values.
I was thinking some of the techniques they're using, they don't account for like an intervening matter that they don't know about yet. So that could be a reason for margin of error.
So which one? Sorry, which technique?
Maybe the one with the red giants, because since they're using visual for that. Well, I've heard about dark matter recently, and how that's
Hey, you didn't hear about dark matter before?
I've heard about it before, but now I've spent an entire few hours studying it.
Oh, okay. Okay, cool.
And I was thinking, well, that we're learning more about that, and we're going to have some satellites up there this decade studying dark matter between galaxies and in galaxies. What if that's having a big effect on some of these techniques that they haven't bothered to account for yet?
Okay, so actually that's a really great idea. So did everybody hear that? Can anybody argue why dark matter would or would not be a big effect on this? Anybody have an argument? Is dark matter, so actually before we go any further, does everybody know what impact we see dark matter having on the universe? Okay, I'll tell you what, I'm going to make this a question on your participation quiz today. What is the impact of dark matter? Why do we need to have this stuff called dark matter? Okay, it'll be a one quick question. Who knows the answer to that?
I'm not sure how to answer that in one quick question.
Oh, okay. All right. Well, so all right. So
gravitational lensing. That's
yeah, actually, gravitational lensing is one of the ways that we see dark matter. That's correct, right? That's one way. But actually, the answer to the question, the quick question, is dark matter has a gravitational effect.
Oh, yeah.
Right? It has a gravitational effect. And in fact, that's why we think it's there, right? The gravitational effect. It may also have other effects, but the biggest and probably the expected effect of dark matter is to gravitationally lens and alter the direction of light. Okay, so just for everybody else, if you didn't know, let's go ahead and bring up a quick little slide. There was a woman named Vera Rubin who started studying galaxies and the way that they rotate.
Oh, that blew my mind.
You know this, right?
Yeah, I learned it yesterday.
You learned it yesterday?
Sure did.
But you already knew about it, I hope. No, you took the...
Yeah, I had known about it by talking with people about it, but I watched
Oh, you didn't take my lecture before.
Nope.
Oh, shoot. Oh my gosh. Yeah, we got to talk about it then. This is actually really fun. Okay, so take a look right here. Okay, so, oh my God. Well, then actually, this is worth a question on your final exam if you don't know about this. This is actually pretty amazing. So if you take a look right here, this is, so there's a woman named Vera Rubin. I don't know if she's in here. I'm sure she is. Control Vera. Oh, hold on. Just so you know, there was a graduate student by the name, oops, okay, Vera. There she is. In the late 1960s, early 1970s, Vera Rubin was a graduate student, an astronomer at the Department of Terrestrial Magnetism. Oh, I didn't know that. At Carnegie Institute in Washington. I did not know that. But what she was doing is she was measuring what is called the velocity curve of a spiral galaxy with better accuracy than ever before. Okay, so let's just kind of try to understand what that means. And I'm going to show you a galaxy which you're seeing on edge. Okay, so if you saw the whole face of the galaxy, like a spiral galaxy, it would look something like this. But if you look on the edge, right, it looks more like this, right? This is an edge on. All right, so we're looking at the edge of the galaxy instead of down at the top like this. But the galaxy is rotating, like our Milky Way is rotating, and And actually, there's a really crazy thing I'm not going to have time to talk about, but it seems like all galaxies rotate with the same periods. I'm not talking about it, but you can go look that up if you're interested. Okay, so if I'm looking at a galaxy, one of the things that you want to understand is this is what Vera Rubin did. She actually studied the movement of stars within the galaxy by looking at the edge of this galaxy right here. And so I want you to try to imagine that I'm looking at this galaxy and I see I've given you this rotation direction. So what about a star that's on this side of the galaxy? Is it going to be coming towards us or away from us? Which one would it have to be based on my diagram?
Towards.
It's got to be coming towards us, right? Now, you might think about this. If the galaxy is rotating, right? These are going towards you, right? So if you look at a star and the star is coming towards you, what happens to the light of that star? How is it changed? The Doppler effect, what's it called?
They're all blue shifted.
It's blue shift, yeah. We see a blue shift on this side. If you look right at the center, what kind of shift? Is it coming towards us or away from us?
Oh, it's galaxy, so it's going to be red shifting away.
Okay, so just ignore that effect for a moment, though. And I'm just saying, relative to us, if this was not moving away from us, what would we see? You'd see no shift. Now, Lonnie's right. Actually, everybody is moving away. So that is on top of the effect that I'm talking about right now. And then on this side, all of the stars are moving away. Oops, I do too many. Okay, so these would be what? Redshift. So she could measure very carefully the blue shift and the red shift and know which direction the galaxy was rotating. But you can also calculate from the amount of the blue shift or red shift how fast. Okay, so if I were talking about not a galaxy, but a solar system, right, with the sun in the middle, solar system. Make sure you have a little picture of a solar system. Our sun's in the middle. Does anybody remember how solar systems work, right? If they have 100% of the mass in the solar system, what percentage is inside of the star? What percentage of the mass is inside of the star in our solar system? The
99.
sun. It's 99.86% in our solar system is inside of the sun, okay? And the rest is all the planets, an asteroid belt, Kuiper belt, anything else. It's just this fraction of a percent, 0.14% is in orbit around the star, okay? So what happens? Well, as you get further away from the sun, the force of gravity gets weaker. And so we've studied this already. It's one of Kepler's laws. As you move away from the star, okay, the planets travel slower. Why? Well, because the force of gravity is weaker. If they traveled as fast as they did here, they would actually escape. They'd get away. So in order to be bound and have an overall energy which is negative, they have to go slower the further away they get from the solar system. And so when we first looked at these galaxy rotation curves, sorry, let's write down her name, Vera Rubin, galaxy rotation curves. Okay. She looked at these rotation curves. She said, well, you know what? Galaxies look a lot like solar systems. I bet it's the same way. Most of the mass is in the middle, and that all the stars in the disk have to rotate slower the further away you get from the center. And so she said, I expect this, right? This is a solar system kind of story, right? If this is the velocity and this is the distance from the center. Okay, you expect that it goes slower the further away you go. But what she found out was that they don't slow down and maybe even go a little bit faster. The actual, so this was predicted, expected, and this is the actual. curve. And so does it slow down? And the answer is no. And therefore, our whole story about galaxies is wrong if we think it looks like this. That's just not correct. It's impossible. In fact, what this seems to imply is that the force of gravity doesn't get weaker. It may even get stronger the further away you get. That is bizarre. How do you do that? And the answer is you can't have the normal distribution of matter like you do for a solar system. You have to have something else. Okay, so back to the Wikipedia, because they'll show you a little picture, I hope. Let's see. So what she found is that they go, oh, so back to this initial picture. Do you see it? So this is what she expected, that the velocity would fall off. And what she found was something different, right? It either got the same speed or even a little bit faster as you get further away from the center. Okay, so this is actually from another galaxy. This is called the Triangulum Galaxy, Messier 33, I believe. I think so. I might be wrong about that. Okay, so what happens? How is this possible? And the answer is we can't see all of the matter. Oh, let's just look at this animation. This shows you a picture with and without dark matter. Okay, so as you can see, this galaxy is rotating slower on the outside and faster on the inside. It looks different than this one. This one, let's try it again. Can you guys see it? This one is rotating much faster on the outside. And the reason is you can't see the matter that's causing the gravitational field. You can't see it. It's there, it must be there, or else these stars would fly away, but you can't see it. And so it's called dark matter. Okay, so let's take a look right now. Okay, so an unfortunate fact is, oh, where is it? Come on, dark matter halo. I can't see it. Okay, hold on. Dark matter halo. Images. I'm looking for a picture that I like, but I don't know. I don't know if it's going to be there. Okay. I don't see a good picture. Well, okay. Maybe something like that. I don't know. There's dark matter throughout the galaxy, but actually a huge sphere of dark matter is present around the galaxy as well. And in this way, you can explain the rotation curves, okay? So she said there's got to be dark matter. And then here's the problem. When she did the models, dark matter, oh, I know, I moved my camera. Dark matter is required to keep galaxies from flying apart. If galaxies are stable, we need this gravitational field. The only problem is if you consider the makeup of a galaxy, right, 100% of the mass of the galaxy, right, which includes matter that we can see called luminous matter, right? What fraction is dark and what fraction is luminous? So there's luminous, which means you can see it, and there's dark, and it means you can't see it. Now, it could be, by the way, that it's just, not shining with light, right? We'll talk about that in just a moment. Okay, so unfortunately for us, it turns out to make it work, you need to have 90% dark matter. So would you write that down so you know that 90% of our galaxy is made up of stuff that we can't see, okay? Now, some of this might be simple stuff that not simple, but things that we have talked about. For example, the neutrino. Neutrino doesn't shine with light. They're very difficult to catch, right? It does not interact strongly with regular matter, right? And that's why you have these flying through your body right now. And so this is actually probably part of dark matter, but probably only 5% That's the best calc. That apparently, it's only accounts for a small fraction of the dark matter. And so I want to just share with you just a brief overview. Then there's two major candidates, and one of them is no longer a candidate. But the two major candidates are machos, and the other one is wimps. Okay. So these were the two candidates that people came up with in the very beginning. This one stands for massive, compact, halo object. Okay, massive, compact, halo object, macho. And the other one is weakly interacting, massive particle. Okay, so WIMP, right? Okay, so what about machos? What is that, right? So you need a massive object, which is very small, and you can't see it, doesn't shine with light. Can anybody think of anything that behaves like that? Anything you might have studied in this course?
Black holes.
Of course, right? Yeah. And when this first came out, honestly, I think everybody expected that this was the answer. Duh, right? We have black holes whizzing around our galaxy everywhere. They must be all over the place, and we just haven't paid attention well enough to see them. There are black holes everywhere, and this is the reason why galaxies don't fly apart. There are black holes flying around everywhere, everywhere. Now, it doesn't just have to be black holes. It's anything else that's very compact. It could also be neutron stars, although they do tend to glow, but they are very compact. They're very small, right? So it must be the black holes, duh, right? Oh, bam, there's black holes everywhere. The only time we can see the black holes, unfortunately, is when they're feeding, right? The only time we can see a black hole is when they're feeding. Well, actually, somebody figured out something important, right? We mentioned a minute ago this concept. If we're on Earth and we're looking for black holes, obviously, if a black hole is feeding, right, it has an accretion disk, and that shines with X-ray light, right? We can see that, right? The accretion disk. But what about a black hole that's not feeding, right? Suppose there's a black hole over here, right? How do I see it? So the answer is, what happens if the black hole happens to fly in front of a galaxy, a distant galaxy, right? What would happen right there? Or even a star, but anyways, let's talk about a distant galaxy. Would it block the light of the galaxy because it's in front of it?
No.
No, it wouldn't, right? Well, actually, what if the light tried to go straight? Would it block it?
I think that light's gonna get swallowed.
Yeah, of course. This gets eaten by the black hole, of course. But you mentioned it before, Lonnie. What's the concept?
The gravitational lensing.
That's right. What about rays of light that are like here, right? Normally, they would totally miss us, right? They just go off and miss us. But because of the gravitational effect, they are curved and boop, like that. They are actually gravitational lensing, right? Gravitational lensing would allow us to see the light. In fact, you get something very interesting. It turns out that if the alignment is just right, you get a flash. And this is a flash of light. This is really funny. And so theoretically, it's true, and experimentally, it has been verified. It's called a micro-lensing event. Okay, so this is what a micro-lensing event is. The light of that galaxy, instead of being blocked, is actually concentrated for just a moment, and we see a bright flash of light from that event. And so as soon as we understood this, and by the way, this is being done around the world today to detect black holes as they fly in front of other objects, and it works, it works, it works. We can see things in this way. This gravitational lensing is real, okay? But when they went and studied something that's actually really close to us. They actually studied, I don't know the paper, but you guys might be able to look at it. Andromeda, and Hubble was the one that stared at the Andromeda galaxy, which is huge, right? They studied the Andromeda galaxy, and they looked at the Andromeda galaxy for days and days and days, and they looked for these micro-lensing events to occur. And I think there were some, but there should have been, if there's black holes whizzing around, there should have been a huge number of the micro-lensing events. And so even if they saw one or two, they didn't see thousands, which is what they expected, right? And so the lack of micro-lensing from this experiment in particular, it's been repeated, by the way, events, implies there are no black holes, or not very many, not enough black holes. There may be some, but this is not the answer. Macho is wrong, right? The macho idea just doesn't work. It should have led to these. We can't see it. It's wrong, okay? So we're left with one more category, right? And those are called Wimps, right? And the idea is, what does the W mean, right? What's the W?
Weak.
Weak, right? The weak nuclear force. So here's what we know so far, right? Dark matter interacts through the force of gravity, for sure. Check. We know that. It does, right? It holds galaxies together. We need it. If we don't have it, galaxies rip themselves apart because they're moving too fast. Gravity is definitely a part of the interaction, okay? But what about the electromagnetic force? So what's electromagnetic force remind you of? What's the force carrier for the electromagnetic force?
Photon.
The photon. So when you say electromagnetic force, what does it mean? Does it interact through the electromagnetic force? Well, the answer to that question is, can we see it? And the answer is no, we can't see it. It doesn't interact through the electromagnetic force. Are you following? Right? We've eliminated, this is not part of the interaction. The dark matter, whatever it is, does not interact through the electromagnetic force. Now, people have also claimed that if it were to interact through the strong nuclear force, there would be a strong signal that we would see, for example, in nuclear decay processes. And it turns out we have decided, and I don't know all the research behind this, but we have decided that this is not possible either, okay? So we've eliminated these two as mechanisms by which dark matter interacts with normal matter. But we are hoping that we have an interaction through the weak nuclear force. And so the answer is question mark, maybe, right? That's actually what so if you go look up dark matter experiments, they are doing calculations to see how does the dark matter interact, not through gravity, because we already know about that, but through the weak nuclear force. And if there is some effect, we're hoping that it changes the outcome of the experiment when the dark matter is present. But the idea is dark matter is everywhere. It's everywhere. It's not just, you know, far away. It's actually passing through us, right? It's passing through us right now. And like neutrinos, it is just not interested in regular matter. Okay, now I really got off on a tangent. That's okay. That's a really fun tangent. Okay, so dark matter, great. I'm glad we talked about that. Let's go back to our story though, because what we really wanted to figure out is what's the big difference between these different techniques for measuring the Hubble constant, and in particular, the difference between the Planck data and then the telescope data, which is also, Planck is also telescope, sorry, but comparing Doppler effect with microwave background radiation. Anybody? There's a big difference. Okay, so I'm going to tell you, go ahead. Anybody got an idea?
I was thinking the Big Bang cosmic background radiation has got to be a lot older, right?
Hey, excellent. Very good. Okay, so I believe that one interpretation is to understand that these are different time regimes, right? The Planck is dealing with cosmic background radiation. The Big Bang, it's based on the old, it's based on the oldest possible state of the universe, right? The Big Bang. And so in some sense, it probes the early universe, right? The Planck may probe the early universe. And then the Doppler effect measurements that we're seeing are probing much late, well, not only later, but sometimes much later, right? If they're very close to us, we're talking about things that are only a few million years away, okay? And not billions of years away. Unfortunately, we do see the same effect billions of years away. So I'm not sure if it's completely sewn up that this is the reason. But one of the solutions, so if I ask you a question, what is a solution to the paradox that we're seeing right now, right? The data doesn't seem to agree. One solution might be that the Hubble constant has changed. And just so you understand, I am predicting, I'm telling you right now, that if this is the case, then we can also start thinking about the future. If it's changed from the beginning of the universe to now, right, then you would predict what? What would you predict?
You could predict that it's either speeding up or slowing down.
It will continue to change, right?
Yeah.
Exactly. And therefore, what does that mean? Well, so actually what's really interesting is the Hubble is used to determine the age of the universe. So all these pundits, these cosmologists who tell you the universe is 13.8 billion years old, right? 13.84, I don't know, whatever the number happens to be. What's going to happen in the next few years? If you guys please pay attention, this is the fun part, right? The fun part of our course is we're predicting now something that's going to happen in your life. As the value of the Hubble constant changes, our age of the universe changes as well, okay? There's some other little issues that I didn't get into. There's something called, you guys could look it up if you're interested, the Methuselah, how do you spell that? Methuselah, I don't know how to spell that. Methuselah star, Methuselah, anybody know how to spell it? You guys know what I'm talking about? Methuselah. Oh, I spelled it wrong. It's Methuselah. Okay, all right, Methuselah star from the Bible. Okay, let me go ahead and, I misspelled it. Let me go ahead and put the right spelling for you. Okay, Methuselah. Okay, Methuselah star. And here's the question. You can read about it, right? Do you guys see the problem? Look at this Wikipedia article. Age 14.46 plus or minus 0.8 giga years. Do you guys see the problem? It appears to be older than the universe. Okay, which I think is kind of fun, and I didn't really want to talk about it, but anyways, these are some of the issues. So okay, so there is this this issue that we seem to observe where the Hubble constant is no longer agreeing. Now, the hope is actually one of the really cool things is this new technique of gravitational waves may lead to the best measurements of the Hubble constant ever, right? And so we may see that, like Lonnie was saying, that we may be having problems with our visuals, right? Our optics are just wrong. We're missing intervening material, we're mismeasuring. I mean, I hope that's the answer. If that's the answer, then we find out everybody agrees and we have a consistent picture. And, you know, the story is a great story. It's kind of like me believing in the end that the Planck length, that we have a quantum universe, that space-time is quantum, and that in fact there is a minimum distance, right? And if the singularity is that big instead of 0 big, I don't have a problem anymore. My life is much better. I think we're going to see that. Well, I don't know what we're going to see. Actually, I can't predict that. I actually suspect that maybe we won't see that happen. I suspect that what we're seeing is that the Hubble constant has been changing and will continue to change. So, that's kind of like one of the last things I want to leave you with, this uncertainty. We don't quite know yet what's going on. And it's kind of, again, I don't want to make you feel like we don't understand anything. We certainly are understanding more and more than ever before. But the picture is a little bit muddied, right? We can't say clearly, what did the expansion of the universe look like? Has it been uniform? And in fact, one of the things we suspect is that the expansion of the universe is accelerating and is not slowing down the way we expected. And therefore, we have to explain that. So one of the explanations is Einstein's cosmological constant. And we call that, anybody remember the name for that? Expansion, dark, we call it, the lambda, that's the lambda. But the name for the reason that we give is that it leads to a repulsive force between things, this expansion. As it expands, space-time fills it with extra energy, and that energy is called dark energy, right? It's coming from somewhere, right? Because energy cannot be created or destroyed. How does that work, right? Where's it coming from? Where's the dark energy coming from? The answer is, oh yeah, right. I have no idea. Another universe? God? I don't know. I have no idea. I don't know the answer. Okay, so that's fun. I hope you enjoy that. And then I want to share with you, anybody have any comments, questions? No?
Comment.
Yeah. Okay, Lonnie, yeah.
I love that. That was awesome. It really pieced together some of what I learned too. And I know I'm excited.
Cool.
All
right. So I mean, the truth is that what we have does fit together pretty well, but you're starting to see where it doesn't quite match. And now, there is an interpretation. Could be the Hubble constant is changing, but that might not be right either, right? Maybe that's not quite the right interpretation. Anyways, I wanted to share with you something. Some of you might have had Professor Mike Young as a faculty member. If not, he's a great guy, and he teaches physics. If you want to take physics, I recommend Michael Young. He's really good. Although Doug Folsom is really good too. Amy Thompson is really good too. So if you take physics here at CC, you can really learn some good stuff. One of the cool things Michael Young has done is he puts his lectures on YouTube. So you can actually learn physics without even being enrolled in a class. It's calculus-based physics, but depending on where you're at. All right, so but he and I have been in debates in the past. And one of the issues I actually want to bring up is a question Paul Irwin had last week, and I missed it on the YouTube, and I totally messed up. I'm sorry, Paul. Okay, but Lonnie, you got onto Zoom. Okay, so anyways, but Paul Irwin asked the question. Let me write it down, okay, because I think it's such a great question to ask, okay. If a galaxy is receding from us at a z greater than 1, right? How do we see it? Does everybody understand the question? And why it might be interesting? If something seems to be moving away from us at faster than the speed of light, then how can we ever see it?
We can't.
Does it seem like a good question? I mean, would you like to know the answer? Or no? Maybe you're not interested. Okay, although I don't know why, because I find it incredibly intriguing. My brain is a little bit warped thinking about this. But remember, Einstein originally had the story, his Gedanken experiment was, he was in a room traveling at the speed of light at a constant speed, right? Would he see his reflection? And we said yes, right? Because he wouldn't know that he was moving at the speed of light, and therefore the light would bounce off the mirror and he would see his reflection. But this is a little bit different, right? We understand that the reason for this is because of not from special relativity, but general relativity. This is a general relativistic effect, general relativistic effect. You cannot do this in a single frame of reference. You cannot do this. It's not allowed. But in the view that we have with our space-time stretching, this is allowed, right? Okay, so I want to share with you a really cool article. I put it on Canvas for you, and this way you can read it for yourself. In fact, I don't know if you should read the whole article. It seems like it might be a little bit long. I forgot. I mean, it's been a few years since I've read this. So let's take a look. The article is from Scientific American, 2005. So if you click on the link, you can download. I already downloaded it. Okay, so let me just open it. And here, can you guys all see a blank piece of paper right now? Okay, here it is. So here it is. The title of the article is Misconceptions About the Big Bang. So you're not alone. Baffled by the expansion of the universe, you're not alone. Even astronomers frequently get it wrong. I probably have gotten at least some part of this wrong. So if you read this article, if I screwed you up a little bit, you can get back onto the right track and understand it properly. But the fact is, I still am confused by some of these ideas. Okay. And I don't even, I don't know, I'm not an expert at this, but I have a problem. So it's 11 pages. Can I ask you to read 11 pages? I don't know. Oh, there's pictures, lots of pictures. Okay. So we have a little sphere and then we have a big sphere, expansion of space-time. What happens as a result of this picture, right? The further apart things are, the faster the distance between them will appear to grow, because every unit is growing. The more units you have, every unit is growing. Actually, does that make sense? Let me just pause for a second right here. So if I take a grid, right, and I imagine, you know, some different things right here, you know, 3 different things right here. If I consider the distance between here and here, it's 1 grid space, right? And the distance between here to here is 2 grid spaces. But what happens in the expansion of space-time is the space between the points is getting bigger, right? And so what was, you know, actually, so it's still going to be 1 or 2 grid points apart. But what happens as a result of that, right? Well, this distance increases by however much the grid has increased. But the distance from here to here, each of these grid lines has gotten bigger. And so it's actually twice as much of an increase because of this bigger distance. And if I went 3, it'd be 3 times as much of an increase, right? So the further away you go, the greater the difference in the distance will appear to be. This is exactly what Hubble's equation is supposed to be showing you, right? This is why we believe this, okay? That space-time metric expanding leads to this effect right here. Okay, so anyways. So yeah, so the expansion of the universe may be the most important fact. Okay, so this is gonna be too much stuff to read in one thing. But let's go ahead and jump to this little square right here, cosmic confusion. The expansion of the universe is one of the most fundamental concepts of modern science, yet one of the most widely understood. The key to avoiding the misunderstanding is not to take the term Big Bang too literally. The Big Bang was not a bomb that went off in the center of the universe and hurled matter outwards. Rather, it was an explosion of space itself that happened everywhere, similar to the way the expansion of the surface of a balloon happens everywhere on the surface. The difference between the expansion of space and the expansion in space may seem subtle, but has important consequences for the size of the universe. The rate at which galaxies move apart, the type of observations astronomers can make, and the nature of the accelerating expansion that the universe now seems to be undergoing. Strictly speaking, the Big Bang model has very little to say about the Big Bang itself. It describes what happened afterwards. Okay, so blah, 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 blah. I wish I could just get to the hard part. Okay, so here, okay, here, this is actually kind of what we wanted to talk about. So let's just do this one square here. So can galaxies recede faster than light? Wrong. No, of course not. Einstein's special theory forbids that, right? Consider a patch of space containing some galaxies. The galaxies move away from us. The farther the galaxy, the faster its velocity. If light speed is the ultimate limit, the graph must eventually plateau like this, okay? And this is wrong, okay? Why is this wrong? Because this is what special relativity says. The theory of special relativity says this. And in fact, it doesn't apply when the spacing is getting bigger. So the answer is, yeah, they can, sure, no problem. Special relativity does not apply. In expanding space, recession velocity keeps increasing with distance. Beyond a certain distance, known as the Hubble distance, it exceeds the speed of light. This is not a violation of relativity because recession velocity is caused not by motion through space, but by the expansion of space-time itself, okay? So this is a weird idea. It gives us the perception that the object is moving away from us, but in fact, the object is not even moving in some sense, right? It's not even moving. It just looks like it's moving because space-time is expanding, right? Okay. So here's, I think we're going to get to something. I wanted to talk about being able to see it. Okay, here, this is it. Okay, so this is the set, and I may be having to finish pretty soon. So, can we see galaxies receding faster than the speed of light? Of course not. Light from these galaxies never gets to us. A galaxy farther than the Hubble distance recedes from us faster than light. It emits a photon, the yellow squiggle. As space expands, the photon is dragged away like someone trying to swim against the current. The photon never reaches us. And the correct answer is, well, yes, we can, and we do, right? We do see that. These photons initially are unable to approach us, but the Hubble distance is not constant. That is weird. Okay, and can grow to encompass the photon. Once that happens, the photon approaches us and eventually reaches us. So in other words, the photon in this very distant galaxy, as it goes through the first portion of its journey, it may actually appear to be moving away from us instead of coming towards us. But the idea is that once it gets to this region where we're within the Hubble distance, then we will see it coming towards us. After all, it will be shifted in frequency because of the the redshift that we expect from general relativity. But in fact, it eventually does get to us. Okay, so this is confusing. And does every photon get to us? What if it's receding at 20 times the speed of light? Can it still get to us? And actually, this author talks a little bit more about it. Let's skip this part. Actually, this is a funny thing. Is Brooklyn expanding? That's funny. Is our galaxy expanding, right? And the answer is no. It turns out the expansion doesn't happen within the local group or within our galaxy. It only expands at bigger distances, right? So we don't see expansion everywhere. We see expansion outside of our local group, okay? And then how large is the observable universe? This is my last point that I have available here, I think. So we'll go ahead and finish off with this. The universe is 14 billion years old, so the radius of the observable part of the universe is 14 billion light years. That's wrong. That's incorrect, okay? The correct answer is because space is expanding, the observable part of our universe has a radius of more than 14 billion light years. What had to happen is the light had to leave at some point in the past to get to us now, and the maximum time we have is 14 billion years. But currently, that could be as much as 46. It may even be larger than that. So something that is currently 46 billion years ago, in the past, when the light was first emitted, it was much closer to us. It was within 14 billion years of us. Okay, so this is the point that I said. Do objects inside the universe expand too? Yes, expansion causes the universe and everything in it to grow, but the answer is no, it's not the same everywhere. It turns out that the local group stays together, but outside the local group, the expansion is significant. So there is no expansion in our local group, or almost none, I guess. And then outside is where the expansion is really happening. Okay, so if you're interested, I would encourage you to take that article and try to understand it. There is a limit to how fast they can go, though. I don't know what the limit is. I think I read it in this article once upon a time. I don't know, maybe this article doesn't answer the question. But I would suspect that there is, in fact, a maximum speed that you can still perceive, right? So even if a photon manages to get into the Hubble distance and can then propagate to us, if it's far enough away from us, that light will actually never reach us. Okay, so what does it mean for us? What does it mean for us? What does it mean for the future? In the future universe, it's kind of sad, but I have 5 minutes to tell you a sad story. In the future universe, we will one day no longer be able to see distant galaxies. They will start to disappear. They will either redshift away or be so far away from us and expanding so fast that the photons from those galaxies can never get to the part of the galaxy that we can see. And so the universe will go incredibly dark when you look beyond our local group. Our local group will stay together, though. So we will always have our local group to keep us company. But eventually the light of galaxies must fade, right? When the last star dies for our local group, then the universe will eventually go dark. The end of the universe will be dark, right? Except it'll be filled with light, very low energy light, okay? But other than that, it will be dark. Wow, what a depressing thought. But it's very, very far away. We're talking maybe even hundreds of trillions of years from now. All right. Any comments, questions? I think that might be all I have to share with you today. But anyways, so we have a final exam, and I mentioned to you that I'll open it on Monday morning and I'll close it on Wednesday evening. Please get it done before then. I have a lot of grading. I'm kind of behind on so much grading. So if you notice grades missing, please don't worry about it unless Wednesday comes around and you check your grade. When I tell you to check your grade, by the way, you should definitely check your grade. If you see anything missing, please let me know. We have a week to figure it out. There are also a few quizzes. You might have missed a quiz because you were absent from class. And because of our weird situation, I don't have an opportunity to see you guys again. I do want to find a way to make up at least some of those quizzes. Okay, so if you want to make up a quiz, please send me an email saying, I missed this quiz, can I make it up? And I will make something on Canvas for you to try to do that, okay? So I do need to get an email from you because I have so many other things to do. If you're not interested in making it up, then I don't want to waste my time making it for you, okay? But if you want to make it up, I want to give you that opportunity. Okay, so it has been a great pleasure to be your teacher. Thank you guys so much for being here. And I hope that, you know, at least something of your brain realizes that there's so much more to learn. We can't possibly ever be done. We could live forever and we'd still not be done. And I hope that you continue to be curious and look for stuff. Oh, I have something else. Wait. There's one more tiny little thing. Last night, has anybody seen the Starlink satellites in the sky? Anybody seen them? Can I recommend that tonight you try to see them because they are so cool. I mean, maybe one day they'll seem ordinary. Has anybody seen them? Anybody? Yes, no, maybe.
I've never spotted any yet.
You haven't? Oh, wow. You are in for a treat. It's so crazy. My son, Connor, and I were watching them. It's like for 5 minutes, the string of satellites went across the sky. It was amazing. I'm serious. You should see this. And I'll show you right now how to get there if you're interested. Just give me 1 second. I will show you a great website for this. Okay, so this is the website that I used last night, and it worked really, really well. Okay, so I'll put a link for you if you're interested. So you go like this. Find the star link. It's really crazy cool. Before you can figure it out, you have to put in a latitude. So I would suggest latitude and longitude. I would suggest going. I don't know. Maybe you could just do this. Never mind. No, that's not what you want to do. I would just go to maps. Oops, maps.google.com. You put in your current location. You click the map where you are. I happen to be at school, so oh yeah, there I am. Right, I'm right. Actually, I am really. Yeah, that's actually, wow, that is so amazingly precise. That is amazing. Okay, that is in fact where I am. And if you click, it shows you the coordinates right here. Okay, can everybody see those? 34 for this number right here. Control C that. And then I'm here. Okay, so there's my latitude, and my longitude is right here. Okay, and then I find visible times, and tonight is going to be a good one. Oh, you guys should look for it tonight. Okay, so I'm serious. You will, and this will be good too tomorrow night. So tonight or Friday. Sorry, this is Friday.
You missed a
Friday.
negative sign with your longitude.
What's that?
You missed a negative sign with your longitude.
Yeah, that was west. I took it away. So negative means west. So take away the negative. Sorry. Yeah, you don't need that. Okay, so, and actually here are the details. It's going to start in the northwest. So if you don't know how to find Polaris, that could be a little bit tricky. But anyways, northwest, about 293 degrees azimuth. It's actually pretty close to where the sun is setting. So if you look for where the sun sets in the sky, that's actually where it's going to begin. And it's going to last for 4 minutes. We actually watched for 5 minutes. So I don't know about you guys, but it is really fun to see. It's not going to be super high in the sky, but you will see a train of satellites that just goes on and on and on. It's unbelievable. It's really weird how cool it is. It's just neat. So you need to put in your location, or else you won't get the right times. But I think it's going to be pretty close for almost anybody in Santa Barbara. So I would suggest tonight is a really good opportunity. Okay, so thank you guys so much. I hope you have a wonderful day, and good luck with all of your final exams, and good luck in your futures. Okay, so thank you guys. Thank you. All right, good. I'm glad you enjoyed that. Thank you. Anybody on YouTube want to say anything? You could say something. Hello. Okay. No, Lonnie, you're in Zoom. Okay. So I'm done. That's it. Anybody else? Thank you. Thank you for being here.
Thank you, Sean. I really enjoyed this class.
I'm glad. Thank you for being here. I'm really, really grateful for all of you guys, especially coming to the Zoom, because without you, I would feel very lonely. It's much harder to just talk into a computer monitor. So thank you guys for being here very much. Okay, so thank you, and have a great day, and have a wonderful week. And I'm around, and hopefully, we'll get over the quarantine. And by the way, after the quarantine, I'm planning on doing star parties as much as I can. So if you're around and you want to come and look through the telescope with me, please do. Okay, you're always welcome.
Heck yeah, star parties. Thanks, Sean. This was like my favorite class.
Thank you. I'm so glad you were here.
Yeah, same. This was such a fun class. Like, so fun. Thank you.
You're very welcome. Thank you guys for being here. All right, and I'm sorry it was a little bit rough at the end, but anyways, you guys did a great job and you stuck with it. So everybody who stuck with it, you're gonna be fine. Okay, don't worry. I'm sure the grades will be fine, actually. I'm probably gonna be a little easier in my grading, by the way, just so you know. You don't have to worry about me failing people. I'm not interested in failing people. So if you stuck with it, thank you. You're gonna do fine. All right, well, have a good day and bye.